Hello, welcome to a tutorial on conducting demand-side sensitivities. Specifically today we are going to learn how to add a demand-side technology. So demand-side technologies are technologies that consume energy in the performance of satisfying energy services. And energy services can be anything from heating water to driving a mile. And so these are the technologies that consume that energy and then perform that service. So today we're going to do kind of a silly example here. We are going to add a residential water heating technology, and today we're going to add a cauldron as a residential water heating technology. So we are here in the demand technologies table, and as you can see, we have around 250 technologies all represented in the model. The first step is to determine the subsector that the technology resides in, so basically the end use that it satisfies. We know we're in residential water heating. I've cheated a little. I know that's the ID 33, but if we wanted to, we can look that up in Navicat and determine, 33, residential water heating, okay. Next up, we determine the name. The name doesn't matter, it merely represents how the technology will be represented when it's output, so any text will work. Following that up, we actually need to determine the lifetime of the technology. So Energy Pathways, one of its principal strengths is the stock rollover dynamics that it contains. That means that we have to understand the way these technologies roll over. So we need to determine two things. One, which way do we want to determine the lifetime? We can determine that with a minimum lifetime of the technology. So what's the minimum amount of years it can last and the maximum amount of years it can last, and the model uses those parameters to determine a decay function along with an additional parameter that we'll get to in a second. Or we can determine what is the mean lifetime of that technology's life cycle. So the whole population, what's the average time to failure, basically, and then the lifetime variance. So what's the variance in that mean lifetime? Here you can input a source for the technology. So where are you getting this information? Any additional description is also available. This is really for your own benefit. It doesn't actually get used in the model or report anywhere, so it's just good for managing the database. Following that up, we need to actually input the unit type. So Energy Pathways has the ability to model a demand technology either as equipment or as service demand. So it's really easy when we have something like a water heater. It's just a piece of equipment. We can count those. It's a sort of very easy calculation. On the other hand, for things such as commercial lighting, the stock and the unit of that stock is actually the service demand itself. So for example, lighting, maybe have a stock in kilolumens per hour. So basically a capacity, but we don't need to get into that right now because we have a pretty obvious piece of equipment of a cauldron. So I'm going to put one. Sorry, I skipped ahead and forgot to put a minimum lifetime and a maximum lifetime. I don't know how long cauldrons last, but probably 75 to about 150 years, I would say. Pretty rugged. So the unit, we can actually call that water heater because that's really what it is. It's the cauldron is the technology, but the unit of the stock is water heater. And then this stock decay function is the final parameter for determining the stock rollover that I was discussing earlier. If we go here, we have three options. We can either have a Weibull decay, so the shape looks like a Weibull distribution. The second option is linear, so if the average lifetime of the technology is 10 years, we just decay from 0 to, in this case, would be the whole stock would decay in 20 years, so that the average lifetime is 10. But it's just a straight line decay of that stock. Finally, lump. For some of these big investments, specifically on the supply side, we actually want them all to decay at once. An example of this would be a nuclear plant. You install one, it doesn't decay incrementally, so in that case it would be lump, and that would just use the average lifetime to decay it at one point. So a cauldron, we're going to use a Weibull because it's really a population of cauldrons, and assuming they decay at different rates. So we have stock decay function 1. These parameters to the right, shape ID, max lead hours, and max lag hours, are parameters that we will discuss in other tutorials. So now that we've defined demand technology and its main characteristics, we need to define some of its performance parameters, performance in terms of cost, performance in terms of efficiency. So we are going to first go to capital cost. So if we go to the capital cost table, we have the demand technologies referenced here that we've input capital cost for. We need to choose our demand technology from the table. I've already forgotten the ID. 302. I will remember that for next time. So the demand technology is 302. The definition ID, this can be absolute, which is ID 1, or relative, which is ID 2. So we allow a user to input technology definitions either as an absolute value or as a value relative to another technology. So for the relative value, it's a little more complicated. What this means is if we had, say, a technology that was expensive cauldrons and we input the capital cost of that, and we're doing a technology of cauldrons and we want to use a relative cost, we could say, okay, a cauldron is always 50% the cost of an expensive cauldron, which means we would input a value of 50% so that whatever the cost of the expensive cauldron, this cauldron's cost would just be linked to it with that value. We don't have that. We want to input it as an absolute here, so we will choose definition ID 1. There is no reference technology, as I said, because we are doing absolute. The geography ID is actually exposes another feature of Pathways. We have the ability to define technology parameters on a variety of geographical indexes and sort of an infinite amount of geographical indexes, but it is related to the values that you have in your geographies table. So in this case, we are doing a US model and we want to define cauldrons across the US. They all cost exactly the same. Probably a reasonable assumption. So I know the geography ID of the US is 4, so I will put that here, but I will also look at the other geographies to show you exactly what our other options are. So say we wanted to input cauldron costs on a state basis, we'd have the ability to do that. Obviously, that is more helpful for some things than others. The second thing that we have in terms of describing the data are these things called other indexes. So for some technologies, we actually want to define the costs on a basis other than a total. So for example, in residential technologies, sometimes we want to define costs for single-family homes, multifamily homes, and mobile homes. Those are our other indexes of residential housing. So if we wanted to do that, we would choose the other index of housing types, which is 1, and you can see some of our technologies have that other index. In this case, we're not going to do that. Cauldrons cost the same, whatever the house. So past other indexes to currency ID and currency year ID. What this is if you have values for capital costs, they likely come in a dollar year value. So if you have a study that says the capital costs of solar are $1 a watt, and that study came out in 2015, and it was in US dollars, we would have the ability to choose US dollars, which in this case is ID 41, and say those are in 2014 dollars. So our capital costs of all our technologies get converted to the dollar, year, and currency value. So we have the ability to support around 45 currencies. So everything goes in a certain currency, and then it comes out in a currency related to what you've defined in your configuration file. So in this case, the Cauldron capital cost will be in 2014 US dollars. There is an is levelized parameter. So sometimes the capital costs of equipment aren't in totals, they are in a levelized value. So for example, you may get a cost that says a water heater costs $150 per year. This is usually used on the supply side. Demand side, it's a little sillier, but you may get that. And so the is levelized flag tells the model that that $100 is a levelized value, not a lump sum value. So in this case, it's not levelized. We're gonna say how much the Cauldron costs on day one. The final parameters are related to cleaning the data that you've put in across all of the years. So interpolation method, extrapolation method, and an optional extrapolation growth parameter. So if you put in capital costs for cauldrons in 2015 and 2020, the model is going to need to know how much those also cost in 2021 or 2050, depending on what year you want to run your model out to. So it needs to know how to interpolate between 2015 and 2020 and how to extrapolate past 2020 in this case. And so to do that, we have different, what we call cleaning methods. We have 8 different cleaning methods. So we have an interpolation, a regression, a logistic cleaning method. Nearest is it just chooses the nearest point in time and extrapolates from there. Quadratic fit, a cubic fit, an exponential growth option, and then none, which is used specifically on the supply side, and we can get into how that's used at a later tutorial. So in this case, we are going to do a interpolation method of 1, which is a linear interpolation, and then for the extrapolation method, we are going to do 4, which is nearest. So I'm going to input a capital cost for 2015 and a capital cost for 2020. And so from 2015 to 2020, it will use the linear interpolation, and from 2020 to 2050, it will just use the value for 2020. That's how those cleaning methods get used. So to input the actual time series data, I'm going to go to capital cost new. So we're going to define the cost for a new cauldron. This really comes in for pieces of equipment that cost more to install in older homes than they do in new homes. So sometimes new home construction prices are lower. And so you have the ability to define capital costs separately for new and replacement technologies. But in this case, cauldrons are going to cost the same. And so the model only needs you to input capital costs new, and it will just replicate that for replacement costs as well. So we have demand technology number 302. See, I remembered 302. The GAU ID is the unit of the geography index that you've input. So in this case, we've input geography index 4, which is the US. And so the US only has one element of that index, which is the US. State would obviously have 50, or actually 51. I think we have Puerto Rico in there as well. But in any case, the GAU ID is 65 for the US. So what we're defining is a cauldron anywhere in the US. And so this is how we do that. So vintage is the year in which the cauldron is purchased and installed. So in this case, I wanted to do 2015 and I wanted to do 2020. We skipped the other indexes because we didn't input another index value. How much does a cauldron cost? I have no idea. Let's say 100, and then in 2020 it costs maybe 125. It went up a little bit. So that is how we input the capital cost data, and we're all set. Now, there are other potential costs that follow really approximately the same format as we just went through in capital costs. They're just for different cost parameters, and so the model uses them slightly differently. We have things like fixed maintenance costs, fuel switching costs, and installation costs. So fixed maintenance cost is just $1 per unit per year. So if it costs $10 to maintain that cauldron every year, you would input a value of 10 in the model and use 10 in every year. Installation costs and fuel switching costs are both related to the installation of equipment. So cauldrons are pretty easy to install, but for other things there are additional costs like wiring or piping or demolition of previous equipment, something like that adds an installation cost. And so for costs like that, we would put that as an installation cost. For fuel switching costs, these are costs related specifically to switching the energy type of the end use. So the classic example is switching a water heater from a gas water heater to an electric heat pump water heater. When that switch is affected, actually there is an additional wiring cost so that the voltage can support a heat pump water heater. So that additional wiring cost would be input as a fuel switching cost, because then when that heat pump rolls off in that home, it actually doesn't have that additional wiring cost again because it's already switched to that electric version. So that's how that fuel switching cost would work. The parameters of those are the same as the capital costs. So you input vintage costs, you can have other indexes, etc. They aren't required to be the same geography or anything like that. They can be on different other indexes. So, but the basic structure remains the same. So I won't go into each table. The second class of parameters that we may want to input involve the efficiency, so the energy use of that device. So let's go to the efficiency table right now. That is Demandtech's main efficiency. So there's a principle that we need to explain in the model so that we understand the table names here. So main efficiency refers to, the efficiency of the device when it is using its primary final energy type. So the best example of this is plug-in hybrid electric vehicles. They are effectively dual fuel, but they have a separate efficiency for when they're using electricity and for when they're using gasoline. So that would be input. The electricity would be input as the main efficiency, and the gasoline efficiency would be input as the auxiliary efficiency. In our case, we don't need to worry about that. Cauldrons we're going to heat with wood regardless, and so we can just stick to the main efficiency, but it's important to understand exactly what you would do if you had a dual fuel device. So Demand Technology ID 302, as we remember. Similar to the capital cost, we have the ability to define that as an absolute or a relative. In this case, we're going to define it as an absolute. So definition ID 1, no reference tech because it's an absolute. The geography ID, same efficiency everywhere in the US. No other indexes. This is a new parameter, final energy ID. So this determines how we are actually heating the cauldron itself. So these final energy types refer to effectively linkages to the supply side in terms of delivery of that final energy. So they're all different energy types. We have gasoline, electricity, diesel fuel, pipeline gas, LPG fuel. In our case, we're going to heat that cauldron with wood, so we go to number 6, and that determines when this unit consumes energy. It consumes energy of what type. So second factor over is related to the main and auxiliary efficiency differentiation that I spoke to earlier. In this case, the utility factor is 1. So utility factor refers to what percentage or what ratio of the final service demand is met with this energy type. And so cauldrons are single fuel, so that value is 1. PHEVs, your utility factor will be related to how many miles are electric versus gasoline. Efficiency type, we have a couple of options here. We can use an absolute value or we can use a normalized value. The model can derive efficiency trajectories based on its knowledge of how much energy was demanded at a certain point in time. Primarily, as you can see, we do use absolute values. They're a lot easier to communicate, but we do maintain the option basically of just having normalized efficiency trajectories to affect future energy demands. The next parameter is it's an is numerator service flag. So this is obviously not very self-explanatory, so I can go into a bit of a description of it. Is numerator service means when I have a unit of efficiency, is the numerator of that unit a service demand or is it an energy demand? So for example, if we look at these vehicles and their specifications, the unit is actually miles per US gallon of gasoline equivalent. So in this case, the unit of that is service because the service we're providing is driving a mile, and the denominator is how much energy it takes to get there. If we had instead defined this as US gallons of gasoline per mile, then that flag would be false. And this is just related to how the model interprets your efficiency inputs. So for things like water heating, we want to do BTU out over BTU in. So that is a BTU of a service demand and a BTU of an energy demand. But the BTU out is the actual energy service. That's the actual heat we're getting out of the wood, not the sort of potential energy, chemical energy within the wood. So that numerator would be service. Interpolation methods and extrapolation methods, we're going to do 1 and 4 like we did before, but the principle is the same. These additional new characteristics I will get into. Shape ID is related to the flexibility of the technology, but the age, growth, or decay type and age, growth, or decay. Effectively, some technologies actually decay in terms of the efficiency at which they provide an energy service. And so we allow that to occur by either a linear decay or an exponential decay. So say a cauldron's efficiency decayed linearly, excuse me, I was actually putting in the decay rate. So it decays linearly at a rate of 1% per year. That's how we would input that. That's obviously not true, so we're not going to put that, but that's the method you would use to input those parameters. Now we've basically described the technology efficiency record, and now we have to actually input the data. So we go to the time series data related to Demandtech's main efficiency. Demand technology 302. We're going to do similarly a 2015 and a 2020 look. So, 2015, 2020. And the efficiency of combusting wood to heat water, let's say, is 20%. So, and that's 20% in both years. So really, we don't even need a 2020 value because the model will just use the 2015 value and extrapolate using the parameters that we input. So that's going to be 0.2. There is no auxiliary efficiency because, again, we've set a utility factor of 1. Other technology parameters related to energy use would be parasitic energy and the parasitic energy data table, where we actually input the time series data. Parasitic energy is related to the energy use of a piece of equipment that's not directly linked to the amount of service it provides. So, for example, some furnaces just have sort of an ongoing parasitic load And we would put that in here as electric load. So maybe it has sort of an ongoing cost of 300 kilowatt hours per year. And that's added to the final energy demand, unrelated to the amount of service it's actually providing, so the amount of heat it's actually providing. So that's the parasitic energy parameter. So now that we've done this, we have successfully defined a new technology. That new technology is now available for use in the rest of the model, and that will be the subject of future tutorials, where we get into things like how we add that to a stock, or how we make that technology penetrate the market so that we see cauldrons everywhere heating water. So that has been our demand technology specification tutorial, and I hope you enjoyed it. Thank you.